Hello everyone, my name is Shui Zhang, and my supervisors are Dr. Liang Zhou and Associate Professor Shoudong Huang. Today I'm going to talk about my recent research work, 3D reconstruction of deformable column structures based on preoperative model and deep neural network. The outline including background and motivation, research problem statement, technical challenges, related works, proposed framework, and technical details. The simulation, experiments, and validation using in vivo datasets, and last, the conclusion and future work. Colon cancer is the secondly commonly occurring cancer in women and the third in men all over the world, and colonoscopy is the golden method to detect and remove precancerous polyps and adenomas. However, 22% of polyps and adenomas are missed. The two main causes are the conical mucosal surface was not entirely inspected, and the surface was inspected, but the polyps and adenomas were not recognized. If a 3D column map can be reconstructed during the colonoscopy, then two main benefits can be achieved. First, the missing areas can help doctor to navigate the camera to recover more surface. Second, the textures on the column map can help doctor to inspect abnormalities offline. So our research problem is how to reconstruct 3D column map using the monocular colonoscopy images and show the missing areas on the reconstructed column map. To reconstruct the column map, the following technical challenges should be solved. The depth estimation of the monocular colonoscopy images, the camera motion estimation when the camera moves fast and there is no lab closure to reduce drift. And third, reconstruction with detailed texture and first, column deformation. And the last, the colonoscopy dataset when ground truth of camera poses and depth is critical to validate the proposed 3D reconstruction framework. For related works, shape from shading, stop motion, and approach with restricted substrates are proposed to reconstruct only a segment of column map. And nowadays, the combination of depth estimation neural network and SLAM are combined to reconstruct a 3D column map. But this kind of works cannot handle the deformation and requires consistent slow camera motion, and there are no lab closure to reduce drift. This figure shows the proposed framework to reconstruct a 3D column map. It includes three parts: the first, dataset generation; second, 3D scan reconstruction and camera initialization; and the last, non-rigidization and texture rendering. We developed a colonoscopy simulator which consists of three parts: the column segmentation and the mesh optimization, the mesh texture generation, and last, the 3D visualization and interaction with the Unity. The left video shows the interface of the colonoscopy simulator. We can manipulate the camera inside the column model and capture images. Right video shows different levels of deformation. We make our simulator publicly available. This figure shows a comparison between the simulated and real colonoscopy images. The first and the third are the real images, and second and first are the simulated images. To estimate depth for the image and reconstruct a 3D scan, we use a encoder-decoder network via translearning to estimate depth. Here we collect 10 colonoscopy videos, and each contain about 1K frames when ground truth to train the network. We make our trained dataset publicly available. The figure shows the images and corresponding estimate depths. The first and second are the synthetic images and estimate depths. The third and first are the real images and corresponding depths estimated by the trained network. For a pair of consecutive images, we use the network to estimate the depths and reconstruct the 3D scans. 2D shift matches are obtained for the consecutive images. So we can get a 3D sparse key points by migrating the 2D shift features into their corresponding 3D scans. If the previous scan is well registered to the column model, there will be dense correspondence between the previous scan and the column model. Combined with the sparse correspondence between the current scan and the previous scan, we can extract the sparse key points between the current scan and the column model. This sparse key point will be used photometric constraint. Here we use the embedded deformation graph to deform the skin. We formulate an object function which including 6 terms. The rotation and the regularization term are used to keep the deformation as rigid and smooth as possible. The geometric is obtained by the nearest correspondence between the scanner model. The photometric is obtained by the sparse key correspondence based on 2D shaped features. The global constraint is used to improve the robustness of the proposed algorithm. The biessential coordinates-based texture mapping is used to mapping the texture from 2D text region to the registered areas on the column map. This video shows the optimization and the texture rendering. Compare our work to the state art of slump systems. We collect the column images without deformation because the state art of slump system cannot work on the deformation images. The figure shows the estimated trajectory from the state-art slump system use images from normal continuous screening. You can see the trajectory are not complete and suffer from large drift. Then we use images by moving the camera very slow. We can see from figure that the state-art slump system also suffer from large drift, and their map are not complete, and some maps are complete, but there are just some dense or semi-dense sparse points. The video shows the reconstruction of the column on the plane camera flight path. The top left shows the estimated camera path and the ground truth. The bottom left is the camera view, and the right top is a reconstruct column map, and the right bottom is the camera pose errors compared to ground truth. Also, we collect the images with the column deformation to validate the robustness and accuracy of the deformable column reconstruction framework. The left video shows the camera view with the column deformation, and the right shows the reconstruct column map. After reconstruction, we show the missing areas using the green colors. This video shows the reconstruction of column map using all the 3 datasets with different levels of deformation. We compare our work to the one published in 2019 Mechanics. The compare work uses recurrent neural network to estimate depths and then submesh to fill the depths and compose to reconstruct column map. The first row shows our reconstruct map starting from only less drift, and the second row shows compare work. Their reconstruct map suffer from large drift, and the texture is also not clear. The in vivo datasets are also used to validate the practicality of the proposed framework. The left video shows the in vivo datasets, and the middle right shows the different views of the reconstructed column map. By comparison, our work can recover clear column structures, including column folds and topological shape, but the compare work, their maps are flat and lose most of the geometric structures. We published our work in the 2021 ICRA and the 2021 Transaction on Medical Robotics and Bionics. This work presents a robust framework that recovers 3D shape of deformable column structures and textures. Simulation and in vivo experiments demonstrate the practicality of non-rigid 3D reconstruction framework. In the future, the column reconstruction using one general model for different patients will be investigated for the cases when the preoperative is not available. Thank you for listening.